Welcome to the Battery Testing Mentor podcast. My name is Johannes, and here I discuss all topics around battery testing, battery safety, battery handling. Short, on the point, and with practical advice. Also visit www.batterytestingmentor.com and sign up there for the email update. With every episode, I send out the key takeaways of that episode straight into your inbox. And if you have any questions, remarks, comments, feedback, just hit reply on that email and you directly reach me. Today, we have the second part of the interview with Benjamin. I found it super interesting. Today, we talk mainly about the cell development, the early development when you really work with coin cells. With that, I just want to give the floor to Benjamin and come back later after this interview for a short wrap-up.
Yeah, that is interesting. That brings us directly to the next topic. The topic, it's a huge topic, the topic of battery cell chemistries. And I have to say, you are really into this, you are super experienced. And the topic is as big that it's really hard to find a starting point to talk about.
Yes, exactly. I don't know how interesting that is for your listeners. This then goes into great detail, but we can explain it very briefly, roughly, somehow. So I say, this is the smaller unit. If we have a very large battery pack, you can break it down to the modules, then again to the cell, where we then have just three different types. Of course, there are still some special types. But in general, you have the pouch cell or the prismatic cell, i.e. a box, or then the cylindrical cell, which is really like an AA battery, only large. And if you break it down further, you are at the inner life, at the electrodes, and if you break it down further, you are at the materials, which provide you with the energy, so to speak. The materials are then responsible for providing energy, which is ultimately the energy content of the corresponding battery, and accordingly, I can only say that cell testing itself is not so different from battery testing, in quotes. It is the same, just a whole number smaller. You just don't have huge equipment requirements. You can buy a small climatic cabinet, buy a small saucer, you don't need a huge source sink in your equipment. But the basic tests remain the same. Also the mechanical tests or safety tests, and of course mainly, and much more, we have of course the electrical tests. Whereby it's then just really in cell development, not about the shapes, not just how it looks or how you make it, but really what materials can you take, how do you combine them, and what comes out of it afterwards. And unfortunately, I would say that there is a lot of screening involved.
So basically a lot of trial error. I guess you experiment and try and combine again over and over and try to find something that works.
Unfortunately, yes. A lot of trial and error, and of course there are a lot of approaches. You can make calculations beforehand, I'll say, so you can really use models to see how the corresponding molecules behave, so to speak, and what they would ultimately give out, so to speak. But it has often been shown that the theory then differs very strongly from the practice. It is then ultimately only, I'll say, a hint, a direction.
One thing that I have in mind or remember is that basically you have in the cell the additives as a key component. You have the framework, the graphite, the lithium compounds, and so that in some way make it work. But to really make a difference, to influence the safety, to influence the performance, to influence the lifetime, it's all about additives.
Yes, exactly. So in fact not only. It doesn't necessarily only have to be in the electrolyte, but mainly because it is the easiest to add. But it can also be that you somehow add it to your electrodes, that you produce the electrodes in a certain process and then, for example, coat them again very specially or something else. So there are a lot of possibilities. But yes, mainly it's really the electrolyte. And with the standard system that I told you about before, which we have been using for years and which we will probably continue to use for years to come, despite its obvious weaknesses. It's really like that, there are really appropriate additives for each application. For example, if you want to have lower temperatures, if you want to have the battery safer, more durable, that can all actually be affected and tailored. Of course, this should not be overestimated, because if the basic structure is not right, then the additive can no longer do so much.
As with building a house, if the foundation is not working, you can't do a lot. That brings me to another thought, like, I mean, the question is how much insight you have, but if we go now towards solid state, will like everything change, or is it just bring the additives into the solid material then somehow and continue with the same additives as before?
Yes, there are already some changes. So actually the complete insights I have now not there, for that I make too long no cell testing more. I am honest about that. But yes, it should already be different, because
it's not only you squeeze it together.
Yes, exactly, so there are also a lot of things that come together, because in this case you have to get into the cathode, that is, into one of the electrodes, you also have to get into it, you have to manufacture it very specially and add things so that it works, because the biggest problem is, if you have two solid layers and nothing liquid in between, then the challenge is simply at the interfaces where the particles touch each other. That's where you have the highest resistance, so to speak, and that's where it usually fails. In the past, the system just didn't work, and it was also said that it would never work because of precisely these boundaries between the particles, and it was always said, okay, you can operate this, but you have to make it very warm, because then you lower the activation energy, or, in other words, you facilitate the transition.
So that it kind of melts together. Can you say it this way?
Yes, exactly, in very rough terms. I think there used to be a streetcar that ran on sulfur batteries. They really ran at over 600 degrees Celsius, so it was really liquid sulfur.
Wasn't there once this car, like, I mean, this prototype car with a battery? And the big problem was that you always had to keep the battery at 600 degrees Celsius, which costs a lot of energy, of course. Yeah, it was a Zebra battery, right?
Yes, that's right, those were the Zebra batteries.
Yeah, long time ago.
Yeah, you know, maybe someday it will be dug up again. Someday someone will say, hey, I've got a new idea, and then I'll just sell the old one again as something new.
These are the cycles, right? But if we look now into the cell development, how is this happening there? I mean, you said you have the materials and you need to look into them. If you now have this new idea and new material combination that you want to try out and that is amazing, do you start then by building coin cells with this, or is there even a step before?
Yes, well, we actually built up so-called Swagelok cells back then. That sounds better than it is. You have to imagine it like this. It was simply a T-piece tube where you had the possibility for a reference electrode. If you had the two electrodes here, you could place another reference electrode from above. Because you have the problem that when you build a coin cell, you have a two-electrode system, which means that you only ever see the total influence. You can't look at one electrode at a time. You can only do that if you have a reference, because then you are no longer measuring voltage but real potentials. Then you can really draw accurate conclusions, because you always see the corresponding electrode against the reference system. And
reference is the minus pole?
No, it comes from above, it has to be as close as possible to the counter electrode, and in our case that was always lithium metal. And as I said, the procedure is that you really look in basic research at how these three electrode systems work in order to find out, at which point do I now have my bottleneck. And then you would move on to, let's say, coin cells. When you have a bit more production-ready material, in quotation marks, and then it just gets bigger and bigger. The next step will be pouch cells. And then you will first build a bistack, i.e. the smallest unit, and then you will try to stack it up, because that's the crux of the matter. It's nice when it works in the lab and on a small scale, but it really has to work in a giant system afterwards, and that makes, well, that's a completely different challenge. Like, for example, the current manufacturers who produce pouch cells, these huge pouch cells for the vehicles, these are huge long cells, and then you also have to think about, how do I wet them and how can I design the system, because you really do have different energy densities within the system. If you have a defect somewhere in the system or cracks in the electrode, that is of course the first point where the cell is attacked or where the cell slowly dies from the inside.
So if we go back to this early testing, this coin cell testing, then the sweatshop testing, it's mainly their electrical testing, I guess, just to try out, to find out how long the cell will last, how many cycles, how many 10 cycles, maybe one, how many 100 cycles.
Yes, that is correct, it is done similar to the car industry. There, the standard is set, the cell is considered dead when it has reached 80% of its input capacity. And until then, it should survive at least a few thousand cycles, so you can extrapolate that. So projecting how long the cell will survive, for example 10 years, is just insane, and let's be honest, hardly any cell can do that. Of course, some clever executive will tell you, the cell can do that. Interestingly, such things are very difficult to reproduce, and that is one of the cruxes of cell research. I might say it gently, that sometimes people have invested too much in something, so they can't admit that it's a mistake. Then they just say it has to work. And then the more you believe in a result, eventually you get exactly that result.
Yeah, then you find something that confirms it. Genau, da findest du dann, was das bestätigt.
That was the second part of the interview with Benjamin. I hope you found it as interesting, as fascinating as I did. I have to admit, I'm not really into this early development of cells, like what happens in universities, what happens in battery manufacturers, in the research labs, where really the researchers sit down and build the coin cells with their own hands. So that was really, really fascinating. Also important was really how he said the electrolyte makes the characteristic of the cell. Of course, if the overall thing doesn't work, if the structure is not right, the electrolyte cannot save it. But if the frame is good, the electrolyte can really change the characteristics of the cell. I hope you also took some learnings with you out of this interview. One last remark. If you have any wishes for who I should interview in the future, just let me know or go onto the survey that is still online in the bottom of the email that I sent out. Just click there and there are 2 questions. Just let me know. I'm happy to hear what you're interested in. With that, I thank you very much and see you next week at the Battery Testing Mentor podcast.